Hello everyone, in this video I'm going to give you some background information about an incident wave due to external sources. Abacus provides a type of distributed load for loads due to external wave sources, individual spherical monopole or individual or diffuse planar sources can be defined subjecting the fluid and solid region of interest to an incident field waves. Waves produced by an explosion or sound source propagate from the sources, impinging on and passing over the structure, producing a temporary and especially varying load on the structure surface. In the fluid, the pressure field is affected by reflection and emission from the structure as well as by the incident field from the source itself. The incident wave loads on acoustic and or solid meshes depend on the location of the source node, the properties of the propagating fluid, and the reference time history or frequency dependence specified at a reference, which we call it a standoff node. So here in this picture, I'm going to make it bigger, you're going to see that this is going to be the source node that we're going to define the explosion to this point, and this is going to be the point that we call it a standoff point, and this is a standoff point distance, and here this is going to be an acoustic mesh, and then we're going to have a layer of fluid surface and solid surface, which is going to be the structure mesh in the middle. So in Abacus explicit, the Conweb model can be used for an air blast loading on a solid and a structural element without the need to model the fluid medium. If you remember, in the first section of this course, we talked about the air blast. So if you remember, in that place we used the Conweb model, and there we didn't need to model any fluid region. But in under water explosion analysis, for instance, a ship or submerged vehicle subject to an underwater explosion loading, the fluid is also discretized using a finite element model to capture the effect of the fluid stiffness and inertia. For these problems involving both solid and acoustic element, two formulations of the acoustic pressure field exist. The first one is a total wave. The acoustic element can be used to model the total pressure in the medium, including the effect of the incident field and overall system response. The second one is a scattered wave. The acoustic element can be used to model only the response of the medium to the wave loop, not the wave plus itself. So here, the distinction between the total wave formulation and the scattered wave formulation is relevant only when the incident wave loads apply. This is very important. So the total wave formulation is more closely analogous to a structural loading than the scattered wave formulation. The boundary of the acoustic medium is specified as a loaded surface, and a time-varying load is applied there, which generates a response in acoustic medium. This response is equal to the load acoustic pressure in the medium. But in the scattered one, the scatter wave formulation exploits the fact that when the acoustic medium is linear, the response in the medium can be decomposed in a sum of an incident wave and the scatter wave. So in the total wave formulation must be used when the acoustic medium is nonlinear. So scatter wave is used when we have a linear behavior, and here for total wave we use a nonlinear. So for the example that I'm going to solve for you, I'm going to use a total wave. So now the scatter wave formulation description. When we can use this model, when the mechanics of a fluid can be described as linear, the observed total acoustic pressure can be decomposed into two components: the known incident wave and the scatter wave that is produced by the interaction of an incident wave with a structure and fluid boundaries. When this superposition is applicable, it is common practice to seek the scatter wave field solution directly. So when we're using a scatter wave formulation, the pressure at the acoustic node are defined to be only the scatter part of the total pressure. Both acoustic and solid surfaces at acoustic structure interval should be loaded in this case. So for the total wave formulation, this model is particularly applicable when the acoustic medium is capable of cavitation, rendering the fluid mechanical behavior nonlinear. It should also be used if the problem contains either a curved or a finite extent boundary when the pressure history is prescribed. Only the outer acoustic surface should be loaded with the incident wave in this case, and the incident wave source must be located exterior to the fluid model, and any impedance or non-reflecting condition that may exist on the outer acoustic boundary applies only on a part of the acoustic solution that doesn't include the prescribed incident wave field. So which means that when we define the non-reflecting or any impedance at the initial condition, we need to deactivate that when the explosion happens and when the wave is created. So thus the applied incident wave loading will travel into a problem domain without being affected by non-reflecting condition on the outer acoustic surface. So normally when we using this model, in the first condition we define the environment as a non-reflecting before explosion, and once the explosion happens we need to deactivate that, so then this wave can travel into a domain without any problem, as I mentioned here. So now we have a different type of incident wave. So if you go here, if you remember, we had the air blast in the first part of this course, and surface blast is pretty similar to the air blast, just is on the surface. Now we have three more options here. We have a planar, a spherical, and diffuse. So the first one is a planar. Planar incident wave maintain a constant amplitude as they travel in space. Consequently, the speed and the direction of the travel are the critical parameters to define. The speed is defined in the incident wave interaction property definition, and the direction is determined by the location of the source and a standoff point you define as a part of the incident wave interaction. The second one is the spherical that we're going to use for the next example and in this section that I'm going to explain more in the next slide. So now let me just explain the diffuse part. Diffuse are characteristic of reverberant spaces or other situations in which waves from many directions strike a surface. For example, reverberant chambers are constructed intentionally in acoustic test facilities for sound transmission loss measurement. Okay, so now the next one that we're going to use that we normally use this model for explosion underwater is a spherical incident wave. For a spherical incident wave definition, the wave reduced in amplitude as a function of space. By default, the amplitude of the spherical wave is inversely proportional to the distance from the source. This behavior is called acoustic propagation. For the preferred interface, we can modify the default propagation behavior to define a spatial decay of the incident wave field. So specifically for definition of a spherical, we have three options. We have acoustic, we have UNDEX charge, and we have generalized decay. So for the example, what we're going to use the UNDEX charge because we can provide more information, such as bubbles that it created after explosion. So when explosion happen underwater, it creates bubbles, and in UNDEX charge model we can actually give the parameters for that one. So I'm gonna explain the parameters that we're gonna have in UNDEX charge. So what we're gonna have, so if I put the model as a spherical and UNDEX charge, we need to provide three parameters: physical, material, and bubble model. So the first one is physical. That is we need to provide a gas specific heat ratio, and then we need to pull acceleration due to a gravity, atmospheric pressure, flow drag coefficient, flow drag exponent, and also we can neglect a wave effect in a fluid and gas to neglect a wave effect, so we can just deactivate this one. The second one is going to be material. that we need to provide the material property for the explosive part. So as you can see, we have the constant KKAB, and also we have a adiabatic charge constant, density of charge material, and mass of charge material. And finally, the information about the bubble model. So here we need to provide a time duration. So the first one is it's the time which you take for a bubble to be created after explosion. Normally it's a very small, and then we need to define the maximum number of the step, and then relative step size control parameters. These are normally default, that is defined by Abaqus, so we don't really need to change any of these parameters. The only thing we need to change is the time duration for the creating a bubble. So here, as we can see, we're going to have a spherical model, and we're going to have a source, and again standoff point, and also we need to define the surface as well. So basically, the incoming wave load is further described by the location of its source point and the reference point, which is here, and point where the wave amplitude is specified. So basically, this is everything about what we're going to use. Of course, there are a different way of applying acoustic explosion in Abaqus, but specifically for the tutorial in this section, I'm going to use a spherical model and in an UNDEX chart. So basically it's going to be the explosion under the water, and then we're going to see the effect of that on a different application. Thank you so much for watching this video. I hope this video helped you to get some idea about what we're going to do in the example. Thank you for watching.